Good morning, everybody, and happy Earth Day. Today, we're going to continue our notes on electricity and focus on current electricity. We're no longer going to be stuck in the area where we're just charging up a capacitor or moving individual electrons on one surface to exert a force on another. Now we're going to talk about what happens when we have those electrons move with a purpose in a given direction to power something, and that is the world of current electricity. At the end of the notes, we'll have a chance to do a little bit of history and determine what the name of this shadowy figure emerging from the lightning is right down here. But more on that later. That'll be for story time. For right now, let's move on with the idea of current electricity. Electricity is best, I think, discussed in terms of analogies. So I want you to think of electricity, or current electricity, like a river. All right, a river of flowing current. So there's our first step. When we talk about current electricity, moving water is going to be your analogy, at least the very first bit. All right? And when we see a stream or we see a river, one of the first things we notice is how much water is flowing. How fast is it moving? And the same thing can be said about current electricity. We're going to think about how much is flowing. And that flow rate we call current. All right? So current is going to be measured in amps. On the next screen, you'll see that amps are going to be a unit represented by a capital A. Current is charged particles which flow from a voltage source through a conductive material like wires and through something you're going to power all the way to an electrical ground. All right? So current is how fast things are flowing. And again, we're going to describe it in particular ways. The unit for current, and current is represented by the variable I, as you can see right here. All right? The unit for current is the ampere. Again, capital A. So I is the variable for current. A is the unit. It is a fundamental unit. All right. It is a way of describing how many particles are moving by a certain point on a wire in a given period of time. It's derived from coulombs, which we already talked about. That's how we would measure charge. It's the measurement of the flow rate of charge, and that's where this equation right down here comes in. So current is equal to the number of charges that pass a particular point in a given time. So take that down too. When we are working with current and we're working with circuits, we're going to measure current with an ammeter. Now we already used a voltmeter before, a multimeter in the classroom, right before we had to change to this format. This is the exact same meter. We're just going to switch where we plug individual pieces, like that little red wire will be plugged into a different place, and we'll have the dial set to something a little bit different. But it measures current in amps. And this symbol right here is what we would use on a schematic if we're making a circuit and we want to measure current someplace. All right, so that is called the ammeter. So if current is going to be how fast particles are flowing through a circuit, what makes them flow? If we're talking about water, we're talking about going to Niagara Falls, and we see all that water rushing over the falls. Why is it moving? Gravity. Gravity. It's just trying to get closer to the center of the Earth. So what makes a current of particles, charged particles like electrons, move? Well, that push is our voltage. All right? Again, we've called this voltage, we've called it electrical potential, potential difference. In the end, it's really the source of the force that makes current flow. All right? So again, focusing on this idea of using water as an analogy, I have right here a little water system like what maybe somebody has in their house if they have a well. We have a pump, we have a valve, we have a water pipe, and the water pipe gets kind of narrow right here. Maybe it's going to a faucet or something like that, or maybe going to something even smaller, just a small hose. Then it comes right back here. If we're talking about water moving, the pump is going to push water molecules through this valve, through this area right here, and all the way back. The only reason the water is moving is because of the pump. It provides a force to move it. In electricity, it's not very different. Instead of having something like a valve, we're going to have a switch. Instead of having this area where the water flow is kind of constricted, we're going to have a resistor. But instead of having a pump, we have something like a battery source, a source of voltage. You close that switch, it allows the current to flow. The current will flow as the particles are pushed at a certain rate by the voltage source. All right, so current, that's how fast things are moving. Voltage, That's a way of thinking about the push behind that current flow. We're going to describe it a little bit more here. So voltage is an electrical potential difference, again, a term we've used before, between 2 points on a conducting wire. We measure voltage in volts. We already know that. Voltage comes from various sources. 2 examples might be something like a battery, like little battery that allows the spark. In this thing, got a small battery back here that goes to a piezoelectric. So it's not so much the battery that causes the arc as much as me pulling the trigger. But I also have the battery in something like my phone. That would be a voltage source. But we also have voltage sources right over, well, on the wall behind me. I have electrical outlets. Same thing. I'm getting a push from those. But just because the push is what makes that current flow, it doesn't mean those 2 sources are going to push the exact same way. Batteries and electrical outlets both provide a push, making current flow through a circuit, but there is a difference in the way that push is applied. And that's what we have to focus on next. And it's using something we've all heard of before, but what does it mean? By that I mean AC versus DC. Yes, I'm making a joke about the band. Let's skip over that. It's more funny when it's in person and I can play some music in the background. But we're going to leave it alone for right now. I want to know what is the difference between what we're going to call alternating current and direct current. First, which one do you use to power a majority of things in your home? Now, depending on what you're watching this on, your answer could be a little bit different. But if we're talking about something like refrigerator or a clothes dryer, they're not going to run on the exact same thing as, say, my calculator here, which runs on batteries. The batteries provide what we will call a direct current. Now, direct current, as you can see right here, is kind of like a steady pulse. It goes in one direction, and one direction only. It's produced by things like batteries, as we said before, fuel cells, solar cells. Current always flows in the same direction from a negative terminal to a positive terminal. That's how we're going to describe it, for our purposes at least. It is a push by voltage from one point to another point of different electrical potential difference. All right, it flows kind of like the water flows downhill. The voltage source pushes current in a direct current system in a given direction. All right, now how is that different than something like that washing machine or the refrigerator or the clothes dryer? Well, those are going to run on alternating current. And I use right here the Simpsons as a great example. So how do we get power from the Simpsons power plant all the way to, say, your home? Well, that's alternating current. It's the name given to the electrical current going from whether it's Niagara Falls where you're getting your power, or the power plant in Oswego, or a coal plant, or even a plant that burns trash, maybe some of those windmills that are up in the Tug Hill Plateau. You're getting current sent to you via alternating current transfer. Regardless of how it's being generated, because that's a different story, it's being sent to you via AC. Now, the direction of current is going to reverse. Instead of having direct current flowing in one direction, we have alternating current, which changes, goes back and forth. And it goes back and forth in specific cycles. It alternates 60 times per second here in the US, or 50 times per second in Europe, and in different rates in other places, depending on who set up the network. A wall socket in the US is going to give you 120 volts at 60 hertz AC power. All right, that is alternating current. So direct current flows in one direction. Alternating current goes back and forth. I would like you to focus on something real quick. Just look at one of these little dots that's representing the electrons being pushed back and forth in this alternating current system. Notice that little dot isn't really traveling from one place to the other. It's alternating, yeah, back and forth, but it's not like it's zooming from one side and back, one side and back. It's really just experiencing a little push from that voltage going this way and then reversing course. Whereas with the direct current back here, it's actually slow progress in one direction. So if we move forward again and take a look at this, I want to actually focus on how the electrons are moving. So we'll take a look at this video. Now in our DC power source, notice these red dots representing the charges are moving at a constant rate all the way along the circuit from one terminal to the other. Eventually, one that starts here will end up all the way on the other terminal. Also notice the direction of flow is a little bit different than how we're going to describe it. This is defined the exact same way that it would have been defined by Benjamin Franklin back in the day. Let's just take a look. So current flowing along the system in one given direction. It doesn't happen incredibly fast either, I want you to notice that. So direct current, constant flow, one direction. Eventually the electrons will go from one terminal to the next. AC, it's not the same thing. These electrons are just shifting back and forth, and then back and forth. And they shift back and forth faster if we change the cycle. If we make them cycle faster, cycle slower. The only way to get these electrons to move quicker is actually to apply greater voltage. We could apply greater voltage to this side too and make them move faster as well. Or we could make them alternate faster, which would also increase the speed of the individual electrons shifting back and forth, making a higher current. Now that's something that's going to be manipulated later and comes into play with the next part of our notes. And for that, well, it's story time, and I have to set the scene. First, you have to set the scene and get the field kind of right. So it's dark, and I've got a candle. Imagine right now, let's go back in time. The year is 1856. The Civil War hasn't even started in the United States yet. And we're in Serbia. And you know what? Like any good story, it starts with, it was a dark and stormy night. And it really was, because when this young man was born, July 10th, 1856, his father journaled it. Just like he journaled every other part of his life. As a minister, it was just part of his practice. But on that night, that dark and stormy night, Nikola Tesla was born. Alright? And Nikola Tesla has a life marked with curiosity. From the earliest age, he was just curious about everything, wanting to understand the mechanics behind things, inventing things in ways people didn't quite understand. He would just devour knowledge. He went through all the technical schools he could get into in Europe, and his one dream was eventually to come to the United States of America to meet a wizard, the Wizard of Menlo Park, and hopefully work with him and help him to change the world. Nikola Tesla, from a very young age, was fascinated by the work of Thomas Edison. There are many hops, skips, and jumps in the story from this point on, and there's a lot of conjecture about what really happened and who is to blame and everything regarding that, but there's a simple truth. History is written by the victors, or by the people who can afford a biographer. So we don't have a whole lot of information about Tesla, his early life, or the events that transpired between him and Edison, but I'll tell it to you the way I've read from many sources and the way I've heard it up until this point. Now, he was not going to stay in Europe. He was not going to give up on his dream of meeting and working with Edison. So Tesla did eventually make his way to the United States, and he even ended up working for Edison Electric as a young inventor and a young engineer. A young engineer that was actually so good at what he did that he attracted the attention of Thomas Edison. Now, what do you know about Thomas Edison at this point? Hopefully the light bulb has gone off and you've thought about, well, the light bulb. Edison was a brilliant businessman, and he was an inventor, and I think maybe his business sense maybe even could outweigh his achievements as an inventor. But regardless of all that, he had done things no one ever thought was possible. One, electric light. Not just electric light like arc lights, but electric lights that could be safely put all over places and powered by power generating stations. Edison was a proponent of something called direct current. Now, direct current required huge amounts of copper and a large voltage source to push current electricity through to the light bulbs and light up things like Menlo Park. But the generating of that electricity was inefficient. It cost a lot of money, and he was constantly looking for ways to improve designs. Again, a great businessman. And again, we have this young man right here who's attracted his attention. So, we're going to start off with an interaction that may have occurred, may not have occurred, but many stories say it did. Thomas Edison made a deal with this young electrical engineer and inventor, Nikola Tesla. He said, if you can improve the design and the efficiency of my direct current generator, I will give you $50,000. $50,000 back in the late 1800s, that is no small sum of money. That's a huge amount, as a matter of fact. And Tesla was he was a philanthropist before his time. He was very altruistic. He had these motives of just wanting the world to be a better place. And the majority of the money he made in the U.S. he would send back to his mother. So the promise of this much money just had huge implications for him. So he took on the job. And before long, he came back to Edison with an idea and a plan and a prototype. Now, the weird thing about Tesla is all of his plans were not on paper. They're all inside of his head. He had something called synesthesia. It allowed him to actually imagine things into existence in incredible detail. Say, he thinks about a tree, and you and I, when we think about a tree, maybe we conjure up an image in our mind or whatever, but he would actually conjure up the tree. He would have waking hallucinations where he could walk around the tree and he could see the tree, and it allowed him to actually plan out all of his inventions in incredible detail. And he would work through prototypes and find flaws and failures, and essentially only built things that worked pretty well. He used that skill to improve dramatically on the efficiency of Edison's DC current generator. But he also had that same skill turned towards another idea he had heard of called alternating current. But alternating current is not what Edison had all his plans and money and years of experience behind. So when Tesla presented this improved DC motor and said, but this alternating current generator, sorry, I said motor before, I meant generator. This alternating current generator is so much better, so much more efficient, requires less copper, requires less voltage source, and will be able to provide just as much power, if not more. Now, Edison didn't want to hear this. All right, Edison, by some reports, became enraged, and they had an argument and a falling out. The important part is, at the end of the falling out, even though Tesla had provided this better, efficient, more efficient direct current generator, he was never given his money. And that's where our story takes a turn. We're not just going to talk about two men, but we're going to talk about two men and an elephant in Topsy. And we're going to call this the problem with Topsy. On this side, the gentleman holding the light bulb is, hopefully, yes, you guessed it, Edison, Thomas Edison. On this side, we have Nikola Tesla. And next to Nikola Tesla is George Westinghouse. Now, if we pick up where the idea of these two had a relationship, business relationship, it was fractured. Maybe he did deny him money. Maybe Edison was just a villain and a brigand. Who knows? Okay, we do know they parted ways. And we also know that for a period of time, this brilliant man was so downcast by the experience that instead of going and working more as an electrical engineer, he spent 2 years digging ditches. And as somebody who has been paid to dig ditches before, it's not a lot of fun. All right, it's a little bit different than electrical engineering, but he was just kind of broken by the experience. But he didn't give up, and eventually his idea caught the ear of this gentleman right here, George Westinghouse, who ended up being one of the other investors that would kind of get behind Tesla's idea of alternating current. Until we really get into the specifics of how current is generated, alternating or direct, let's just understand that these are two ways of approaching the same problem, the same idea of providing electrical power to things. One idea is direct current, the other is alternating current. It is not an unfamiliar battle of technologies. If we go back, maybe when you were really, really, really young, we had things called Blu-rays. And before Blu-rays, we had DVDs. One technology surpassed another. And actually, right at that point where Blu-rays were coming onto the market, there was also this ultra high def laser disc kind of thing, and it was kind of like that competition between this high definition recording and Blu-ray. They were two different companies providing the same basic service. And guess what? One of them won, and that's why maybe you know what a Blu-ray player is, but you don't know what that high-def player is. Or if we go back even further, there were these things called video cassettes. And before them, there was something called Betamax. Betamax lost. Wait, Betamax. That's Big Hero 6. It was Beta, which just was the name of it. It was Beta recorders. But either way, technology. There's always a battle, one wins. And now we're going to talk about that battle. Because it was not always friendly. It wasn't just a debate. It was, well, it was a little bit. Edison, this giant of the electrical industry, already had places where he was providing power. Westinghouse and his group wanted to take Tesla's idea of alternating current and do the exact same thing. Basically start up a competing industry. And you know what? When giants compete, they don't usually like it, and they get into a fight. Now this fight was characterized by a lot of different things. Negative press, in some cases it was just out and out lies about the dangers of one versus another. For the most part, Tesla would actually do things like give these insane, mind-blowing demonstrations to people where he would set up huge bursts of electrical energy and just walk safely through it, kind of like what we showed in the beginning. Kind of like this. It would just look like a magic show. He would send up huge arcs of electrical current, and he would walk safely through because he had control of the frequency of the current, and it was perfectly safe. He had an incredible understanding, and these shows wowed spectators, and people would actually come, and it was like going to a concert. You would go to an electric show, kind of like the World's Fair, an incredible experience of the future. Now, because these were very popular, there were certain cities that started to say, wow, this Tesla idea, this alternating current, it's fantastic, and he has absolute control over it. We should go that route. Now, Edison was not willing to just let things go, so he would have people go into these shows, pretend to be spectators, and then when you have this fantastic light show set up, they would start to scream, we're all gonna die, we're gonna be electrocuted, run, get your children out of here. They would set up panic. And, for the most part, that would work from time to time. But plugging away, Westinghouse's group, along with the showman, Nikola Tesla, they were winning people over. And more cities started signing up for this alternating current source, generating stations, to provide electricity to their small cities and towns. It wouldn't be much of a fight if things ended there, though. So, negative press wasn't enough to stop Westinghouse and Tesla, and these little panic experiences in the shows wasn't enough to stop the movement. So, Edison continued the fight by supporting an activist that would always go against alternating current. A man named Doc Brown. Wait, no, not that Doc Brown. He was called Doc Brown, but he was not a doctor. He was actually an electrical engineer. Named Harold Brown. Now, Harold Brown did see that alternating current and people having accidents, basically falling and getting tangled in wires that were provided by an alternating current source, did actually end up getting electrocuted and dying. And that was one of the things that pushed him towards the idea of we have to stop alternating current. Now, he didn't really do a whole study saying direct current can't do the same thing. He was just kind of won over by Edison's debate, and he took up the charge for Edison. And he started working on something that may be a little bit unorthodox, and maybe something that could never happen now. To prove the dangers of alternating current, he took an alternating current generator and modified it, and then put on shows of his own. And remember, people went to see strange things way back in the day, before movies and before concerts were so prevalent. They would go see science shows, and his shows in particular were ones where he wanted to prove on a living organism that direct current was safer than alternating current. Oh my goodness, would you look at the time? You've already been sitting here for nearly 25 minutes. I better stop talking. But what were his shows? And how does Topsy the Elephant play in? And what does this actually have to do with why we use alternating current instead of direct current in our homes? Well, I will upload another video on Friday explaining the rest. Have a good night or day whatever it is when you're actually watching this. Make sure you took a few notes, and we'll continue more next time.